In this example, we're pulling this particle P along a smooth curved guide. We're doing so by putting one end of a rope attached to P, the other end, this force F, which is acting on the end. The magnitude of that force is a constant, and this cord is being pulled over a smooth guide itself. And what we want to know is that if this thing starts from rest over here at position 1, what we want to find out is what speed does it have there at position 2. So let's look at our FBD. What I'm going to do is draw a free body diagram, not just of P, but also of the cord. And we'll talk about why that's a good choice here in just a bit. But if I do look at the forces that are acting on the particle and the cord, the guide is smooth, so the only force that's acting on it from the guide is going to be the normal force in. There's going to be a weight force of mg acting on it. And again, since the rope is part of the system, we don't need to look at the force of the rope on the particle. That's an internal force. But we do have some force here of the guide. I'm not quite sure what that's going to be. I'll call it this point B here. So this is going to be some force there, B, let's say. And then there is the applied force F on the end of that cord, like that. As we look at this, we try to figure out which forces are going to do work, because we have to figure out what forces actually go in U. Well, the normal force in, just by its name, it's normal perpendicular to the path, so it does no work. The mg force, the weight, does work, but we're going to put that in V. The guide force B, which is acting on the cord, it's there, it's real, it's acting on it, it's keeping the cord moving along that line. But being as it's acting at this point that doesn't move, it can't do any work. So all that's left is this force there of F. So when we write down our work energy equation, we'll do it term by term. We're going to have 5 of those terms, as always. It says that the particle P starts out at rest, initially at rest, so T1 is a 0. Potential, well, the only potential we're going to have is due to the weight, so we need to define our datum position. So I'm going to arbitrarily choose to put my datum here at the first position for that block. So with that choice, V1 is a 0. T2, 1/2 mv squared. V2, it's going to be mgh, and we need h there at position 2. We go back to our picture. This is our h2 right here. So h2 is going to be 0.3 plus 0.4. So that's 0.4 meters. That's the number we're going to put in there once we get ready to solve this. Then we look at the work. Now, the reason I chose to put the cable in the system is that we know a lot about the path of the point at which that force F acts. This force F acts on the end of this rope. Okay, so let me call this point A. So this force is going to be pulling the cable out to a new position where A is going to be there. This is where A is, let's say, that's just A. And A is going to be over here at position 2. Okay, it's probably going to be somewhere up here at position 1. So if you look at this, you see that since F and the tangent vector for the path of A are pointing the same way, what we're going to have for the work term is simply force times the distance through which A moves. And we can do this because F is a constant. Okay, so it really is going to come down to kinematics in knowing what distance that this SA is. So I call that delta SA, so I'll put that up there. Again, we'll come back and get that on step 3. So therefore, T1 plus V1 plus the work is equal to T2 plus V2. Starts out from rest, so T1 is a 0. It starts out at what I define as the datum position, so V1 is a 0. So on the left-hand side, all we have is the applied force F times delta SA. T2, 1/2 mv squared. And V2 is mgh2. And one thing I wanted to say but failed to do so is that there is truly a plus sign here. And the plus sign is because it's above the datum that I chose when I began the problem. Okay, so that's a plus. So this is the equation that we need to solve in order to find the speed. The only thing we need to have here is what is delta SA. Because once we have that, we have all the numbers that go into that equation, and we can solve for V. So the question is, how far does A move as a result of that applied force F? I'm going to scroll back to the picture and say that the amount of rope or cord that's being pulled through by that force F is the same amount of rope that's lost on the other side. In other words, if we look over here at position 1, when the block is over here, there's that much cord on to that side of B. So I'll call this length L1. And then at position 2, the length of the cord that's on that side of B is this amount here. And hopefully I can convince you that delta SA, the amount of travel for this position A, this point A, is the difference between L1 and L2. Whatever cord is lost on that side of B is gained on the right side of B. Okay, so let me write that down and then come back up and say that again. So delta SA is equal to L1 minus L2. And we'll get these numbers from our picture. L1 is going to be equal to this side squared plus that side squared. So that's going to be 1.5 squared plus 0.3 squared square root. What's L2? Well, L2, the legs of that right triangle, the one leg is 0.3, this distance there. The other leg is 0.4, so it's going to be square root of 0.3 squared plus 0.4 squared. So that's a number for L1, a number for L2, and therefore we have a number there for delta SA. So when we solve, all we have to do is solve that work energy equation for V. So that's V then is going to be equal to 2 over m times the quantity of F, which we know, delta SA we just found minus mgh2. H2, we know what that is. And we take the square root of that, and that's the speed at position 2. Work energy equation, we looked at the forces that are going to do non-conservative work. We look at our FBD and see that the only thing that's going to do non-conservative work is F. Then we write down T1, that's a 0. Starts out from rest. V1, it's at my choice of the datum, so V1 is a 0. T2, 1/2 mv squared. V2 is only due to the increase in potential due to the increase in height. And the most thinking part of this problem is recognizing that the work done by F is just the distance from where A is at the start to where A is at position 2, delta SA. And we found that by saying the amount of core that's pulled through is the amount of core that's lost on the other side of B. And that's from where we get this. And these numbers come from our figure.